Alrighty, let's begin by talking about clever hands and the law of
Are we ready?
parsimony. No, you're not. You need to find that sheet with the story about the horse on it. How many people have read it already? They couldn't wait for me. The story of clever hands and the law of parsimony. Okay, and you can see there's a picture of a guy in a crazy hat, and apparently he's teaching the horse to do something with a blackboard. So it says, not all explanations for a knowledge claim are created equal. Some explanations involve more details and make more assumptions than others. Assume that you are confronted by two explanations for the same phenomenon. Both explanations seem equally plausible. What does plausible mean? Possible or likely. Which one would you select? The one that involved numerous assumptions and details, or the one that involved fewer assumptions and details? If common sense tells you to select the explanation that makes the fewest assumptions, remember that assumptions also require explanations, then you already have a good understanding of the law of parsimony. Here is an old but excellent example of the law of parsimony. In the early 1900s, Mr. Wilhelm von Osten, a retired mathematics teacher, owned a remarkable horse named Clever Hans. Hans became world famous because he could apparently solve mathematical problems that involved decimals and fractions, tell time, and read, among other remarkable abilities. So basically, the horse could do everything but talk. For example, someone, his trainer as well as strangers, might ask Hans what 7 divided by 4 equals. Hans would tap the answer out with his hoof and receive a treat when he was correct, which was well over 90% of the time. A committee that included the noted German psychologist Karl Stumpf was appointed by the German government to study the phenomenal horse and to prove that his so-called abilities were nothing but a hoax. The committee completed their task and reported that although they were unable to prove that Hans was receiving intentional cues, they remained unconvinced that he was able to solve such mathematical problems and complete the remarkable feats by using his cognitive processes. In other words, they couldn't prove either that the horse it was a hoax, or they couldn't prove that the horse was really that smart. They couldn't come up with an explanation. Stumpf's assistant, Oskar Funks, decided to continue investigating the phenomenal horse. So in other words, they kept going, right? Funks conducted several experiments and concluded that when Hans could see the person asking the questions, he was able to supply the correct answer. If Hans could not see the person asking the question, then his performance fell to near zero levels. In other words, if I asked you a question, okay, if I asked JC a question like this, she can answer it. If I went like this and asked the question, couldn't answer it. Now what's up with that? The horse was reading lips?
I think he was blinking or something.
Funks was faced with two alternative explanations for the horse's abilities. Hans understood the questions and was able to use cognitive processes, in other words, to think, but only when he was able to see the questioner to solve the problems, like he was lip reading or something. But I mean, the guy wasn't giving him the answer. Or that the person asking the question was somehow inadvertently cueing the horse when to stop tapping at the appropriate moment. Applying the law of parsimony, Funks chose the latter explanation. In other words, he picked the one that was simpler and involved fewer assumptions. He chose the latter explanation and persisted in his investigations. He finally determined that almost everyone who asked questions of Hans made a minute upward movement of their head when the correct answer was reached. The horse used this cue to stop tapping and received his treat. This was an instant of positive reinforcement. So when the person would ask the question, and they would probably like hold a finger up at the chart there to show him when his answer was right. And when he got to the point that the answer was right, the guy would go like this, right? Maybe his eyebrows went up or something like that. The horse picked up on that and knew that when the guy's face did that, ooh, I'm going to stop tapping and I'm going to get a treat. The horse was pretty smart, but was he doing math?
No.
No. He was just reading basics. That's a smart horse. If you apply the law of parsimony as you evaluate knowledge claims, you are well on your way to becoming a good psychological consumer. Some additional points to consider as you evaluate knowledge claims are covered in the next section. I'm not going to talk about that. Okay? Please don't take this the wrong way, anyone. Q rays. What do you think about the Q rays? Those magnetic ion bracelets.
You think it works in such a way.
Now, would you choose the assumption that, you know, there's all this scientific stuff that's really kind of hard to explain, or would you choose the explanation that it's simply the placebo effect and it just makes you feel better because you're supposed to? Bingo. Apologies to anyone who has one, because now you're going to stop doing that. Alrighty.
Don't guys sing a song.
The law of parsimony is keep it simple. The explanation that is the simpler explanation that involves the fewer assumptions, the fewer mathematical rules, the fewer exceptions is likely the most correct. And I'll give you another example of the law of parsimony. Okay? You all know that in the good old days, they had the Earth at the center, right? And they had all the other planets doing what? Orbiting around it. The problem was, if they didn't do that, they did this retrograde thing, right? And the sun was making all these crazy, and they had all these rules for when it's here, it does this, and when it's here, it does that. There's all this explanation for how it works. And if they just applied the law of parsimony, which was place the sun at the center, then guess what? Everything was nice and simple. Okay? Classic example of the law of parsimony. Put the sun at the center, and everything makes sense. Okay? All right, let's go back and talk about vector direction a little bit. Okay? Do you think that the pirate activity, you've sort of got a pretty good, solid idea now of how that vector direction stuff works? I think so. It's a good activity for that. It's kind of fun. Let me just sort of remind you of a few things as well. So a vector is a quantity which has both magnitude and direction, as the clip has shown. Examples of vectors include displacement, velocity, acceleration, force. Those are the big four. To fully describe one of these vector quantities, it's necessary to tell both the magnitude and the direction. For instance, if the velocity of an object is said to be 25 meters per second, then the description of the object's velocity is incomplete. The object can be moving 25 meters per second south, north, southeast, or so on. We have to state both magnitude and direction. Oh, yeah. In order for such descriptions of vector quantities to be useful, it's important that everyone agree upon how the direction of an object is described. Most of us are accustomed to the idea that up on a map refers to northward and right on a map refers to eastward. And this is a mere convention which map makers have used for years and upon which we can all agree, right? Does up have to be north? Mr. Dick has a map in his old classroom. I don't know where that map is now, but he used to have a map of the Earth, but it was upside down, right? Is it in his office? Is that okay? It's kind of freaky when you look at it, isn't it, right? It's just a convention, though, right? Is there an up and down to the globe? Like if you go out into space, right? If you go out into space, is this how the Earth is hanging? Only if the Earth hanging this way to look at it, right? If you're hanging upside down, what's it going to look like? And is there any upside down in space? Really? Right? So that's just a convention. North is up. Don't know why. Now, what if the direction of a vector quantity is not due north or due east, but somewhere in between north and east? For such cases, this is important that there be some convention for describing the direction of such a vector. We use the bearing method that has north at 0 with the directions rotating clockwise. And there's a picture of that right at the top here, right? Oops. North is 0. Northeast is at a bearing of 45. East is a bearing of 90, and so on, right? Remember, the only one exception, the mathematicians can't agree. They put 0 where? East, and they go the other way. And actually, it has nothing to do with this. It's a unit circle, and it's completely different, really. So, I don't get the idea that the mathematicians are wrong. They've got their reasons for doing that. Okay? And that's exactly the way navigators on planes work. And there's a link to that down there that I'm going to skip over. Now, you guys, without realizing it, yesterday, were doing vector addition. You were adding vectors. Okay? Most of us are accustomed to the following part of mathematics. How many people agree 6 plus 8 is 14? Hopefully everyone. But what if I told you that 6 plus 8 could also be 10, it could be 2, and it could be 5? It could be any of those. You might not like that so much. You've always been taught it's 14. When we become students of physics and approach the task of adding vector quantities, we soon become aware of the fact that the addition of two vector quantities with a magnitude of 6 and 8 will not necessarily result in an answer of 14. The rules for adding vector quantities are different from the rules for adding two quantities arithmetically. When you add vectors, all the other rules go out of the window. 6 plus 8 will not necessarily be equal to 14. There's one situation where it is. And I know you won't get it just yet. I'll explain right away. I'm in the process of explaining. Vectors are quantities that include a direction. As such, the addition of two or more vectors must take into account that the quantities being added have a directional characteristic. In other words, you have to add the directions too. You can't just add the numbers. You can't just add the magnitude. There are a number of methods for carrying out the addition of two or more vectors. The most common method is the head-to-tail method of vector addition. And let's highlight that. If you haven't been following along, you need to. Head to tail, or I like to refer to it as tip to tail. When you added vectors yesterday, you added tip to tail. Many of you did because you didn't put the arrowhead on, but you were in fact adding tip to tail. Okay? So what does this mean? Using such a method, the first direct vector is drawn to scale in the appropriate direction. The second vector is then drawn such that its tail is positioned at the head of the first vector. So this is what I mean by that. I'm adding a blue vector. I'm going to add a red vector to that, okay? This is the tip of the blue. This is the tail of the red. Tip to tail. Tip to tail. Okay? Is that what you did yesterday? More or less, right? You didn't. One person asked me, do we put all the vectors starting from the same spot? Was it you that asked me that?
Yes.
Okay. What would that mean in a treasure hunt? Like you'd go out and then you'd come back, and then like this doesn't make sense, right? But yet people want to do that when they add vectors. Don't do that. The sum of two such vectors is then represented by a third vector which stretches from the tail of the first to the head of the second, and this is known as the resultant. There's a key word, the resultant. Okay, and I'm going to draw it in black right here. No, that's not black. Okay, it's called the resultant. I wonder if in Despicable Me they'll have a new villain. His name will be Resultant. More powerful than Vector. He's the sum of two or more vectors. You watch and see. You laugh now, but you watch and see. If I was writing that script, how do you think? You've got to think the guy that's writing that script is a physics science nerd, right? When he has the guy named Vector and he puts that joke in there, you've got to think that's coming in version 2. You watch and see. No, I haven't. I'm just. Yeah, you give me a high five. You watch and see. And then, of course, please laugh in the theater when it comes out. Oh, you're not going to forget that. So the sum of two or more vectors is called the result. Now, how many people? I don't know. You probably didn't do it yesterday, but how many people went from like where you started to where the treasure was? Did anybody draw that line? Probably not, right? But would you have to follow all the steps that you did, or could you just go from there to there? You could, right? Right? Like if you were actually following a treasure map, would you have to actually go out onto the island or whatever, do all those steps, or could you do it like you did on a piece of paper, do a scale drawing, and then go, okay, I just have to go over here? You could do that, right? Okay? That would be called the resultant. And the resultant is the vector sum of two individual vectors. Now, the magnitude and direction of the result is dependent upon the direction which the two individual vectors have. Does the angle of the blue and the red have any part of the length of the arc? Absolutely. Right? Like what if I'm going to draw the same, let me just show you here. I'm going to take this one right here, and I'm going to copy that. Okay. I'm going to take the red one, and I'm going to copy that. Okay. But I'm going to take the red one, and I'm going to rotate it. I'm going to put it like that. Okay. Tip to tail. How long is the black one now? Oh, let's do this. Is this going to be the same length? I didn't want to do that. I want to copy that, and I want to paste it. Is that going to be the correct length? Oh, Mr. Bennett. It's going to be close. Well, that's a terrible example. That's a terrible example. Stupid vector. I'll show him. There.
I wonder what the result of that would be.
Me showing him? It's good. Come on, rotate. There, is that going to be the correct length? I think you can see it's not going to be, right? Yeah, that was just a really bad. Get over there. Come on. Well, you get the idea, right? Does the direction matter? Yeah, it does, right? Yeah. All right. That's all I got. What have you got next? Here we go. This principle of the head-to-tail addition of vectors is illustrated in the animation below. Now, I've actually just sort of shown you basically the same thing. In each frame of the animation, a vector with a magnitude of 6 in green is added to a vector with a magnitude of 8 in blue. The resultant is depicted by the black vector, which stretches from the tail of the first to the head of the second. Will this one play for me? No, it will not. Here's that picture in an animated GIF format. You've got the blue vector going to the right, and then the green one is going around. Watch what happens to the value of the black. Let me get it around to the start here. Okay, at the start, it's equal to 14, 8 plus 6. But as it goes around, it goes all the way down to 2, because it depends upon the direction of the green one, right? Depends on the direction of the green one. Now, look carefully at the degrees. What's wrong with that picture? It's the mathematical one, right? To the right is 0, and when it gets to the top, it's 90, right? So for some silly reason, you get a math guy teaching physics, bad idea. Even though that's exactly what I am. Okay, bad idea. All right. So as can be seen from this animation, 8 plus 6 could be equal to 14, but only if the two vectors are directed in the same direction. All that can be said for certain is that 8 plus 6 can add up to a vector with a maximum magnitude of 14 and a minimum of 2. Could it ever be less than 2? No. The only way for it to be 2 would be 8 forward and 6 back, right? That would be the smallest. And the maximum is when they're both in the same direction, right? Okay. Now, I don't think I've got the rest. No, I don't. I'm going to have to do the rest sort of this way, right? What about the order? All I've got is the sheet here now. I didn't finish the slides. You do that. Vector addition. The order does not matter. We proved that yesterday, didn't we? The summative result of two or more vectors can be determined by a process of what's called vector addition. The most common method of adding vectors is the graphical method of head-to-tail addition. This method involves a selection of a scale, like 1 centimeter equals 5 kilometers, and the subsequent drawing of each vector to scale in the specific direction. The tail of each consecutive vector begins at the head of the most recent vector. The resultant vector, the summative result of the addition of the given vectors, is then drawn from the tail of the first to the head of the last one, just like I did back. Where did I do that? Right there, right? From where you started to where you ended. Some people, for whatever reason, like to do this. They like to go blue plus red, and then they do this. And they say that's the result. Vector 1 to vector 2. What's wrong with that? It's definitely going the wrong way, right? Okay? If I told you to walk this many steps and then that many steps, the resultant is where you ended up from where you started. If you go backwards, where do you end up? Right back where you started. Okay? Do not do that. That is wrong. Wrong, 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 wrong. What should happen? From where you start, always to where you end. And then people say, Mr. Bennett, it's not tip to tail then. It's not supposed to be tip to tail. What's supposed to be tip to tail? Just the ones you're adding. Just the ones you're adding. So your result should always be like a tail to tail kind of thing, and the other end should be tip to tip. Okay? All right. Now there's a whole bunch of other mumbo jumbo in here that quite often I just don't need to do. So you know what? Forget it.
Yeah.
Forget it. All right, so let's talk about vector addition. I got 4 sample questions for you that should basically teach you everything you need to know. A car is driven 125 kilometers due west and then 65 kilometers due south. What is the displacement? Now, displacement is a vector quantity. Okay? Let's just draw a little sketch and then try to figure stuff out. So we've got 125 kilometers due west, and we've got 65 kilometers due south. Those are our two vectors that we have to add together. The first question you ask yourself is, are they perpendicular to each other? Do they form a 90-degree angle? They sure do. They're west and south. Okay. If they're west and south, then that means that, do I have to do it by a scale drawing? Because in grade 9, you learned that a squared equals b squared plus c squared, right? Or some variation of that. So what you can do is, right, you don't need, now should you draw them tip to tail? Yeah, you should. In your sketch, you should. Okay? And the resultant is going to be from there to there, right? But in this particular case, I can use the old Pythagoras relationship, right? So I'm going to write r squared is equal to 125 squared plus 65 squared. Right? Now you'll notice, oh, I didn't do it right. You'll notice that I've got a little vector symbol over the r, okay? But I don't have it here. How come I don't? Well, this is the r with the little vector symbol represents the vector, which means it has a magnitude and a direction. Oh, yeah. But this one is just the magnitude part. So we don't put the arrow over the top. This one, when it's just the r without a arrow over top, it's just talking about the magnitude. So now I'm going to write r squared is equal to, and you can solve that. Right? Yes, you're going to require a calculator to do this. No? You want me to tell you a story about calculators in the dark? Yes. Anything? All right, so I didn't actually do it here, did I? 125 squared. 125, come on. 125 squared is 15625 plus 65 squared, 4225. Add those together. Is 198.50. You guys have probably done this already, aren't you? Take the square root. And you get 140.9. And that would be kilometers, right? Can I tell just by looking that it's a reasonable answer?
Yeah.
I got 125 and 65. This number here is going to have to be what? Numerically bigger than these ones, right? Like that distance there has to be bigger than 125, right? Do you think I'm done? I am not done. Do you know why?
Because you got to find angle.
Exactly, because I have to include the direction. I have to include the direction. In other words, what is that little angle right there? And regardless of whether Larissa hates math or not, she still has to do it. So, I'm going to write, now do you remember your sine, your cos, and your tan?
Yes.
Do you remember how to remember them? SOHCAHTOA, exactly, right? And if you don't know what I'm talking about, SOHCAHTOA, sine is the opposite over the hypotenuse, cosine adjacent hypotenuse, tangent opposite adjacent. What situation is this? I've got this one, which is opposite, and I've got this one, which is adjacent. Should I use the value of the hypotenuse here? Like, I do have it. It's 140.9.
No.
You could use it, but, well, you might as well use the ones that are given to you in the question, right? You know that they are true. Okay, so I've got opposite, and I've got adjacent. So it's the tan. Now, am I finding the angle, or am I finding the tangent of the angle? I'm finding the angle, right? Okay, so it's not tan, it's in fact inverse tan that I'm doing. So the first thing I'd like you to write down is theta is the inverse tan. Okay, tan to the -1, that means inverse tan, it means the opposite of tangent. Tan -1, opposite over adjacent. The opposite is 65, the adjacent is 125. You guys tell me what that answer is. Get your calculator out.
Yeah.
What'd you get for an angle?
27.5.
27.5? Okay. Now,
I didn't get that.
you didn't get that? You have to make sure your calculator is set in degrees, right? So now, some of you have the reverse calculators, some of you have the forward calculators. So some of you will have to go 65 divided by 125 equals, and then second function tan. Okay? Others of you can just go second function tangent, then you might get a bracket, and then you can go 65 divided by 125 and end the bracket. Either way, you should get 27.47. 27.47. Now, we could have a big, long discussion about significant figures, but I choose not to. I'm not going to go into my rant this year. But I do know that navigational people, they do not worry. They certainly do not worry about tenths of a degree. They worry about within 5 degrees, and then when they get to the other end, they adjust. Okay? So I'm good with just whole numbers. So let's just round that down to 27. Okay? Just plain old 27. Now, it would be 27 degrees, but what would be the letters that go with it? It would be west 27, south. So west 27, south. Now, a question like that would likely be worth maybe 3 or 4 marks. Probably 1 for the diagram, 1 for that, 1 for, and maybe just probably 1 for the angle. Right? 1 for that. You sure could, yeah. Yeah. You'd have to go, in this case here, you'd have to go 270 minus 27, right? Yeah. I'll have all 3 answers on my page. Okay? Do you want to try one on your own? I think you should. At least draw it out. Take a couple minutes and try drawing it out. Okay, so we've got a shopper walking from the door of the mall to her car. It's 250 meters east. East is to the right. Down a lane of cars and then turns 90 degrees to the right and walks an additional 60 meters. So it should look kind of like that. Is that what you had? Okay. And then the result is from there to there. What is her displacement of her car from the mall door? This is the resultant. This is vector 1. This is vector 2. Is it 90 degrees? Yes. R squared is going to be 200. Wasn't it 250 in the first one too? No. 250 squared plus 60 squared. Now I think you can go straight to R equals. We're all big boys and girls. We know how to square and square root. I'm hoping you do. Okay? I don't need to see every tiny little step. If you want to, you go right ahead and show it. Okay? But it's going to be 250 squared plus 60 squared. If you want to show an intermediate step, you could write R squared equals 66100, and then take the square root of that. 257.1. And that's going to be meters. Yes? Am I done, Sean? No, I'm not. Why am I not done? Got to find the angle. Is it always going to be tangent? Almost always. Almost always, especially in a 90-degree situation here, right? Because it's almost always going to be tangent. So I'm going to write theta equals tan minus 1 of, now opposite is the 60, adjacent is the 250. Yes, Chuck.
So we're always doing like negative 1 though? Like that's always.
That's the inverse. You're always finding the angle, which means inverse tan. Right.
Why don't we use this tan?
Well, because when you find the tan of if you take like 45 degrees and take the tangent of that, then you're finding what's the ratio of the opposite over the adjacent, right? To find the angle, you use invert tan, right? Like really, I'm writing this. I'm writing tan theta is 60 over 250, right? But I need to know what the angle is. So to take the tan to the other side, you do the opposite of tan, which is inverse tan. So it's always going to be inverse tan when you're finding the angle. Okay? So it's going to be second function tan. I say second function tangent, 60 divided by 250. And you get 13.5, we'll round that up to 14 degrees. And what would be the directions associated with it here? That would be east, 14 south. Yeah, making sense? All right. Why do I have a ruler and a protractor on this one? How come I can't do it by a squared equals b squared plus c squared? It's not a 90-degree angle, and yet there will be at least 3 or 4 of you that try to do it on the test that way. This is what people will do. Don't write this down. Do not write this down. 4.5 meters east, 45-degree turn to the right, walk 64, 6.4. This is what they will do. They will do this, and then they will say r squared equals 4.5 squared plus 6. And they'll go r equals, and then they'll go theta equals the inverse tan of 6.4 over 4.5, and it will all be entirely wrong. Why is it wrong? It's not a right triangle. You can't do it unless it's a right triangle. Now, that is an obtuse triangle. Is there a formula for triangles like that? The law of cosines and the law of sines will work just nicely, okay? But if you don't know the law of cosines, now. So the solution is you have to do it by a scale drawing. Let's do this one together. I got 4.5 kilometers east. Now it's a lot harder for me to do it on a scale drawing up here. Okay, bear with me here. I forgot to write my scale. 1 centimeter equals 1 kilometer. And now I got to go 45 degrees. I wish they, actually maybe the new version has, I wish they had a ruler that, .4? Okay, so there's vector 1 and vector 2. And then my result is from there to there. and then I have to bring my ruler in and measure it. I get about 9.7. 9.7 centimeters. Now, because 9.7 centimeter, because 1 centimeter equals 1 kilometer, then 9.7 centimeters would be equal to 9.7 kilometers, and I'm all done. Oh, is it? Oh, it is past 10, isn't it? You're right. Okay, so it's not 9.7, it's 10.3. Right you are. Right you are. 10.3. Now, am I done? No, I am not. I also have to measure the...
You just said you were all done.
I know.
Angle.
I got to measure the angle. I get about 26 degrees. Okay? So that's going to be east, 26, south. Now, are you more likely to be off by a plus couple of millimeters when you do it by scale drawing? Yes, you are. Am I going to give you the same leeway if you're doing it by Pythagoras? Like, could I let you away with 16 degrees? No, it's a mathematical calculation. The answer is 14. Okay? Here, when you're using scale, you can be off by a little bit.
What if we only rounded it to 13?
Then that would be bad rounding, and I would write on it, bad rounding. Oh, okay. Fair enough. While we're at that, let's talk about some rounding, shall we? Because here's a little sort of something that I really hate. Let me do this. Let me write 4 point, let's start with 4. Let's go 5.444449. Is that equal to 5.5? Or is that rounded to 5.4? Which one of those is correct? How many people say 5.4? How many people say 5.5?
It depends what you're rounding it to.
I'm rounding it to 1 decimal place. 1 decimal place. 5.4? 5.5. You do not, I repeat, you do not do this. We're not going to get into that, Craig. I'll save that for another day. You do not do that. If it's 1 decimal point, you simply go 5.44 and you take the very next one and you go. You do not turn that into a 5. You don't do that. You don't, okay? Were you taught that at one time, Luke, do that, do you think? You know? Yeah, because I know that I've heard of teachers teaching that before. That is wrong. It's wrong. Okay. How about you guys try number 4? Try number 4 on your own with a ruler and a protractor. Go.